everybody, how are you doing? Nice to see you today. Last time we worked um, on what? On extrema. Today, and we had the concept of the second derivative. So to make it clearer, if you calculate the first derivative and then calculate derivative of these result of the differentiation, we can have the second derivative of the function. Okay. And it's calculated through the same rules as the first derivative. And we used the second derivative to check if the extrema of the function are minimums or maximums or something else. But today I want to acquaint you with new concept of the second derivative and how it can be used for very interesting analysis of the slope of the function. So I put here the second derivative and slope of the function. And slope of the function, and I add here convex function, convex functions, and concave functions. Okay. Convex function and concave functions. Look, if you use a rectangular system of coordinates here and here, concave functions and convex functions, then a convex function, it has graph like this curve. So if I line here any second line which cross the curve of the function at 2 points, the value of function between these 2 points I denote like A and B. All of them the kind of, for any x's between A and B, f of x is always less than the value of this straight line value. So curve of the convex function at the interval AB is always under any second line which goes through any 2 points of this f of x. For example, if I make the other one second line, the value of the function f of x is always below this straight line. For this situation we say it convex function at the interval AB. Some people say it convex downwards function or concave upwards function. Concave function, otherwise it's kind of, it has a curve so that value that this curve is always up with respect to any second line here. I put here AB. So we say that function is concave function. concave function at the interval convex function concave function at the interval AB. So here we say convex function, here concave function. I drew both of them as increasing function, but it's clear that they can be decreasing. For example, if it is increasing here, decreasing function can be concave, convex, and concave as an increasing function. For example, here we have convex decreasing function because it's still below the second line. And here we have concave function, decreasing function. Decreasing, here increasing. So here convex function, concave. Convex, concave function. Okay. How can we define if the given function convex function or concave function? We can draw a graph, but usually drawing of the graph is not easy. And even sometimes we are disabled to draw the any graph. But we can investigate or scrutinize the slope of the function and derivatives of the function. For convex function, I put here some idea firstly. We can say that the second derivative for convex function is what? Is positive. And here the second derivative is negative. If f for second derivative is 0, function neither convex nor concave. Neither, no, it means that it means its graph coincide with second line, with the second line. How it happens? How do you think? Why convex function has second derivative positive and concave negative? How do you think? The very last thing here, that convex function, I put here two examples. This convex function f of x, the second derivative is positive. Convex function, convex. For concave function, xy, f of x, So for convex function, the second derivative is always positive. For concave function, the second derivative is negative. And it is concave function. Concave. I want to make here a cloud. And here a cloud. So here you have examples on the convex functions and concave function, and here you have a criteria how we can check if function is concave or convex within some interval.